Today we're going to look at using the product property to simplify square roots, including variables. Previously, we've done problems like square root of x to the 8th. And we said we could rewrite that as the square root of x to the 4th squared. We're doing that because square root and squaring are inverse operations. And so if we have something squared and we take the square root of it, we get out the original value, in this case, x to the 4th. We did several of these, and then we started to see the pattern that if we have an even exponent and we take 1/2 of that, we will get the exponent of our solution. So the square root of x to the 8th would be x to the 8 divided by 2 or 4. So today we're going to look at what happens if the number or the variable under the square root has an exponent that's an odd number. 1/2 of an odd number, 1/2 of 11, would be a fraction, but I want to keep my exponents as whole numbers. So what I can do is I can take that x to the 11th and I can break it up into x to the 10th times x to the 1st. I'm choosing to do that because 10 is the closest even number to 11 without going over. And when I write x to the 10th times x to the 1st, by the product rule I'd add exponents, I would get x to the 11th, so they are equivalent. At this point, I can use my product property and split that out into the square root of x to the 10th times the square root of x. X to the 10th is a perfect square. I can take the square root of it, and I get x to the 10 divided by 2, or x to the 5th. And I still have times the square root of x. That is as far as I can go, but it is considered simplified because I found a perfect square factor and was able to evaluate it. Let's look at another example like that. Let's say I had the square root of 100 x to the 19th. Well, when I look at the number part, 100, that is a perfect square. So I will be able to evaluate that. So I'm going to just keep that under there, square root of 100. And I'm looking at x to the 19th, and I say, well, 19's odd. What's the closest even number that I can get to 19? Would be 18. So I'm going to break that x to the 19th up into an x to the 18th times x to the 1st. Now, the first part of this part under the square root, 100x to the 18th, is now a perfect square. So I'm going to use my product property to have the 100x to the 18th in my first radical, and then the leftover x in my second. Evaluating 100x to the 18th, I get square root of 100 is 10, and square root of x to the 18th is x to the 18 divided by 2, 9. And again, I still have this times square root of x in my answer. I'm going to do one more example. And the last example we're going to look at is the square root of 72 m to the 7th. Well, when I start looking at that and I look at the number 72, I recognize it is not a perfect square. So I go over and I start looking at my factor pairs of 72. And what I'm looking for is the largest perfect square factor. And as I start going and making my factor pairs, I'm looking at the large numbers first. I notice right away I get this 36. 36 is a perfect square, and it's going to be the largest factor that's a perfect square. So I'm going to go ahead and start breaking down the number. So in 72, I'm going to write that as the 36 times 2. Now I'm going to look at the variable part, and I see the variable part m to the 7th, so I'm going to break that down into m to the 6th times m to the 1st. 6 plus 1 is 7. Using my product property, I'm going to make two square roots being multiplied, and I'm going to put all my perfect square factors inside the first radical. So 36 was the perfect square part of the number, and m to the 6 was a perfect square factor of the variables. In the second square root, I'm going to put the parts that are still left, the 2 and the m to the 1st. And then finally I can evaluate. Square root of 36 is 6. Square root of m to the 6 is m to the 3rd. and then that's still being multiplied by square root of 2m. And that would be my final answer.